So in our last video, we took a look at finding the area under a curve, which we learned in Calculus 1, so it was just a nice refresher. In this video, we're going to take a look at finding the area between two curves, and our first example is going to use the two examples from the last video. So for our first example, we're actually going to combine the two examples that we did in our last video. We want to find the area between those two curves. So again, in my last video, we found that this first function, f of x, had an area of 18 and 2/3. And my second function, g of x, had an area of 5 and 1/3. So before we integrate this, let's take a look at how we can visualize what's going on. This area is f of x. This area is g of x. So if mathematically I can take, oops, gotta switch back to my pen. If mathematically I can take, to find the area, again from 0 to 4, if I can take the area of f of x, which is from here all the way down to my x-axis, and I can subtract this region, then what I'm left with is this region, which is what I want. So I'm going to take f of x and subtract g of x, all with respect to x. Now, I already know the solution because in my last video we found that f of x was 18 and 2/3 and g of x was 5 and 1/3, and so I know that I'm going to get 13 and 1/3. But let's go ahead and work this out and make sure that's what we get. So we will start again to find the area, integrating from 0 to 4, of f of x, which is, and f of x, I should point out to you, is always going to be the one on the top, whereas g of x should always be the one on the bottom, again, if we are integrating with respect to x, which we are. So here I'm going to take negative x squared plus 4x plus 2 minus 1/4 x squared minus x plus 2 dx. Now again, I want to point out to you that this is subtraction, and I'm subtracting everything in this expression, and so this is where a lot of errors are made. So again, if you have a tendency to forget to change the sign of everything in the second expression, then please write it as plus and change every sign just so you don't forget. So again, I'm still not finding the integral because I'm going to do simplification before I integrate. So I'm going to combine negative x squared and negative 1/4 x squared to get negative 5/4 x squared. I have positive 4x and positive x, which gives me positive 5x, and I have plus 2 and minus 2, which gives me 0. So now that I have this expression, now I can integrate. Again, to find the area, I'm going to integrate x squared, which is going to give me x cubed over 3, combined with that negative 5/4 gives me negative 5x cubed over 12. And then if I integrate x, that gives me x squared over 2. Multiplying that by 5, it's 5x squared over 2. Again, from 0 to 4. So the area is going to be me plugging in the 4. So negative 5 times 4 cubed divided by 12 gives me negative 26 and 2/3. Plugging in 4 into 5x squared, so 5 times 4 squared divided by 2 gives me 40. Plugging in 0 gives me 0 and 0. And so combining this, I get 13 and 1/3. So again, notice I had the same answer as I found doing it separately. Let's do one more practice together where the limits of integration are given to us. So again, we're finding the area between these two curves of f of x equals x squared plus 3 and g of x equals negative x. And those are already graphed for me. So again, this curve is f of x, and this line is g of x. Now we're trying to find the area between the curves from -1 to +2, and so we can see we're looking at this region right here. Just as we did before, we're just going to do subtraction. And again, we're given those limits of integration of -1 and 2. So to find this area, I'm going to integrate from -1 to 2, and I'm going to take the function that is on top, which is f of x, x squared plus 3, and I'm going to subtract the function on the bottom, which is negative x, with respect to x. Just as I did last time, if I'm subtracting, I can make it plus and change the sign of everything in the second expression, which in this case was just negative x. So I am going to integrate from -1 to 2 by doing some simplification of x squared plus x plus 3 dx. So now I can integrate, and again, using the power rule, x squared becomes x cubed over 3, x becomes x squared over 2, and 3 becomes 3x, and we're going from -1 to +2. So now I'm going to plug in those limits of integration, starting with 2. So 2 cubed over 3 gives me 8/3, plus 2 squared over 2 gives me 4 over 2, or just 2, plus 3 times 2, which is 6. And then I'm going to subtract, again, everything in the second expression. So I'm plugging in -1. -1 cubed over 3 is -1/3. -1 squared plus 2 is 1/2. And then 3 times -1 is -3. So I'm going to write -3. And doing some simplification, my first expression gives me 10 and 2/3. My second expression, which I'm going to subtract, gives me -2 and 5/6, and -2 and 5/6. And remember, because I'm subtracting a negative, I'm actually adding. So my final solution is 13 and 1/2. Just as we did before, you can use your calculator to check this. I'm going to skip that in this video because there's already enough for us to go through together. Let's take a look now at our first example where the limits of integration are not given to us. So as you can see, I'm finding the area of the region between the two curves, f of x equals 3 minus x squared, and g of x equals x plus 1. So I can see by graphing this, I'm looking for this region. And again, I can sort of cheat and just look at the graph and see that this is the point -2, -1, and this is the point 1, 2. And so I know that I would be integrating from -2 to 1. But obviously, I'm not going to be satisfied with that solution. I'm going to want to see that you know how to find those limits of integration yourself. And so really all we're trying to do is determine when do those two functions equal one another. And again, I'm only concerned about those x values. So let's plug these in or set these equal to one another. 3 minus x squared, and set it equal to x plus 1. And when we solve this, we should end up with the -2 and the +1. So I'm going to start by putting everything on the right side of the equation. So I'm going to add x squared, which is going to give me x squared over here. And I still have the positive x, and then I'm going to subtract 3 from each side, which gives me -2. So on the left side I have 0, and on the right side I have x squared plus x minus 2. I'm going to do some factoring. I'm looking for two numbers that multiply to -2 and add to +1, which is of course +2 and -1. I set each of those equal to 0 using the zero product property to find that x is equal to -2 and to +1. Notice that is the same two values that I've found here, -2 and +1. This is a necessary step for you to do. From here, again, I'm looking for the area. So all that did for me so far is tell me that I'm going from -2 to 1. Now I need to take whichever function is on top, and keep in mind I've been labeling them for you f of x and g of x, but they're not always going to be labeled properly for you, so you always have to take into account which one's on top. And so in this case, again, I'm going to have 3 minus x squared, and I'm going to subtract x plus 1, all with respect to x. Again, from -2 to 1, I'm just going to do some subtraction. So I have -x squared, I have minus x, and then I have 3 minus 1, which is plus 2 dx. So again, from -2 to 1, you'll find you're doing just a lot of writing and writing and rewriting. If I integrate -x squared, I would get -x cubed over 3. If I integrate x, I get x squared over 2. Notice I kept the negative. If I integrate 2, I get 2x. Whoops. I did not need the integral on that side because I've now integrated, and I'm going to use -2 and 1 as my limits of integration. Again, now I'm just plugging in values. So I'm starting with 1, and I'm saying 1 -1 cubed over 3 gives me -1/3. And minus 1 squared over 2, so minus 1/2, plus 2 times 1, which is 2. I'm going to subtract -2 cubed, which gives me 8, because there's a negative, and a -8, which gives me +8/3. -2 squared is +4, but it's subtraction, so it's -4/2, which is 2. And then -2 times 2 is -4. And I'm kind of out of room here, but when I combine all of that together, I get 4 1/2. So again, that's the area between those two curves. So that added extra step is just to find the limits of integration. Let's take a look now at a more difficult example. I'm trying to find the area of a region between the two curves of f of x equals 3x cubed plus 2x squared minus x plus 1, and that is the one graphed in red, and 2x squared plus 11x plus 1, which is the one graphed in blue. Now, as I can see, the region between the two curves consists of this region and this region. I can also see that I've got 1, 2, 3 points of intersection. Now again, by graphing it, I've kind of cheated and found that the points will be from -2 to 0 and then from 0 to 2. But let's go ahead and mathematically find that as well. Again, remember what we do is we just set the two equal to each other. So 3x cubed plus 2x squared minus x plus 1 is equal to 2x squared plus 11x plus 1. By getting everything to the left side of the equation, I have 3x cubed. I'm subtracting 2x squared, so that's going to actually go away on each side. I have minus x, and then I'm subtracting 11x, so minus 12x. And then I have a plus 1 and a plus 1. So what I have is 3x cubed minus 12x is equal to 0. So I can factor out a 3x, and that leaves me with x squared minus 4, which is x plus 2, x minus 2. Difference of squares pattern. By solving for x using the zero product property, 3x setting it equal to 0 gives me an x value of 0, which I already knew. X plus 2, setting that equal to 0 gives me an x value of -2, again, which I already knew. And then x minus 2, setting that equal to 0, gives me a positive 2, again, which I already knew. But that is how we find those limits of integration. Now, you might be asking, why do I have to have 3 limits of integration? And hopefully you can see why in looking at our picture. We can see, and I'm going to change the color of this one, we can see that in this region, the red function is on top, and in the green region, the blue function is on top. And so that's going to make a difference as we integrate this. So to find the yellow region, again, I'm going to take the top function, which is f of x. So from negative 2 to 0, I'm going to integrate 3x cubed plus 2x squared minus x plus 1 minus 2x squared plus 11x plus 1. And that's going to give me the area of the yellow region. And then the green region, I'm just going to add to that, again, from 0 to 2, this green region, the blue function is on top, so g of x is on top. So 2x squared plus 11x plus 1 minus 3x cubed plus 2x squared minus x plus 1, all dx. And I think I forgot my dx up on top there. I do that all the time, so I apologize. So again, now to find the area, I just need to do a whole lot of simplification. So for my first one, from negative 2 to 0, that simplifies into 3x cubed minus 12x dx. And for my second region, my green region, from 0 to 2, simplifies to 12x minus 3x cubed dx. Again, now I'm going to integrate. This first one goes from 3/4 x to the 4th minus 6x squared from negative 2 to 0. And my second region is 6x squared minus 3/4 x to the 4th from 0 to 2. And I've successfully run out of room here. But my first area is going to give me 12, and my second area is going to give me 12. And so my final solution is 24. Now, if I would have known from the start that the two regions were the same area, I could have just found one area and multiplied it by 2, but obviously that's not clear by looking at the picture. Sometimes it will be clear by looking at the picture and knowing values of our functions that make them symmetric, but in this case it's the best idea to just do all of the work. And again, this is an area, so I should be labeling that as units squared. Let's take a look at one last practice question, and this one is maybe going to hurt your brain just a little bit. So as you can see, I'm trying to find the area between the two curves, x equals y squared minus 2 and y equals negative x. And I've graphed this for you as I normally do, and as you can see, I'm looking for this region. Now, the reason that this one is a little bit tricky is because, as I can see, if I'm integrating with respect to x, I'm going to have a region that goes essentially from here to here, which means the function on top is the first function and the function on the bottom is the first function. And then I'm going to have a region from negative 1 to 2 that's going to give me the rest of this region. And that one would be a little bit easier because obviously that blue line, y equals negative x, is on top. But instead of making this tricky, we're just going to integrate with respect to y. So we haven't done this before, so I'm going to kind of take my time through this one. Now, up to this point, we could always have drawn a representative rectangle going in this direction. But now we're going to draw that representative rectangle going in this direction. And that's going to become more and more important as we move on to volume. But essentially what I'm doing is I'm looking at changing this distance, delta y. So d, that's why we're going to integrate with respect to y. So I'm drawing rectangles with varying widths in the direction of y. Now the reason I'm going to want to do this with respect to y is if you can kind of turn your head to the right, we can think about this function being on top. Again, if I'm turning my head to the right, this function being on top, and then this function being on the bottom. So that's why we do that, because this function is always to the right of the x equals y squared minus 2 function. So just as I did before, I'm going to find those limits of integration mathematically. So I'm going to set the two equal. The first one is x equals negative y, or y equals negative x. Either way, I'm going to actually just rewrite this as x equals negative y. And the reason I'm going to do that is now I have x equals and x equals. So I can say y squared minus 2 is equal to negative y. And now I'm going to rewrite it. So I have y squared plus y minus 2 is equal to 0. I'm going to factor that, y plus 2, y minus 1. And setting each of those binomials equal to 0, I have y equals 1 and y equals negative 2. So that's my limits of integration. Again, integrating with respect to y. So negative 2 to 1. And again, we said that the one on top or to the right is going to be our blue function, which is, again, x equals negative y. So again, this is the format that I'm going to use because it's an x equals form. So I've got negative y, and then I'm subtracting the function on the bottom, or to the left in this case, which is y squared minus 2, all with respect to y. Now, it shouldn't change anything. We're still going to do everything the same way we did before. It just kind of makes your brain work in a different direction. So again, that's the area from negative 2 to 1. If I reduce all of that or simplify it, that's just going to give me negative y squared minus y plus 2 with respect to y, which gives me negative y cubed over 3 minus y squared over 2 plus 2y from negative 2 to 1. Now I'm just going to plug that in. I'm going to get negative 1/3 minus 1/2 plus 2. I'm going to subtract positive 8/3, and then minus 4/2, which is just 2, and then minus 4. The left-hand side gives me 1 1/6. The right-hand side gives me negative 3 1/3. Combining those together, I get 4.5 square units. So again, that's this area between the two curves, and now you know how to integrate with respect to y. So I apologize that video was a little bit longer than I like to make videos, but I really wanted to put everything together in one video for you involving the area between two curves. Coming up next, we're going to take a look at some applications.